So good morning, everybody in this room, as well as those who are online with us. And it's a pleasure for me to welcome here Professor Pietro Michiardi from Eurocom, who will talk about machine learning, more specifically about generative diffusion models, about some ideas, practices, and challenges for the future and application of these in different fields. So now I will leave the floor to Pietro.
Thank you, Zdenek. Well, first of all, thanks a lot for the kind invitation. I'm really happy to be here in CTU. CTU is a partner, actually, of Eurocom, which is the place where I work. And so it's very important for us to keep in touch and collaborate with our partners. So for me, it's the first time I come to CTU. Very glad. Thanks a lot for coming. Thanks for the people online. So yeah, I'm going to talk about a new breed of generative models that actually has taken the internet at a blast. It's something that it's really popular today. These techniques draw some ideas from statistical physics. So at first, they seem to be a bit difficult to approach. And my goal in this presentation is to give you the background, but also to demystify these models, because they actually are super easy to implement, and they can be applied, they have been already applied to a variety of applicative domains. And as a consequence, despite the fact that they seem a bit unapproachable, they are very useful. And I will also talk about some of the work we do in my group. I really squeezed everything in one slide per idea, just not to bother you too much with all these details. Now, this is the menu for my talk. I will introduce what are the problems we are interested in solving, which are mainly generative modeling and density estimation. I will give you a brief overview of the current approaches to address these problems, and then focus on the basic tools we need to develop these kind of new generative models. And in doing so, I will try to give you a bit of an historical perspective, starting from a very important modeling approach, which is called energy-based models. This will give me opportunity to introduce the basic concepts and move to the meat of my talk, which is going to be on score-based generative models. That's where I will try to also go into the more implementation details and tell you how easy actually they are to implement. And I will conclude with three key areas in which we are currently working. Now, if you have any questions, both here, physically or online, please feel free to interrupt me and ask me everything. All right, so let me start with the definition of what are the problems we are looking at: generative modeling and density estimation. So we are given a data set of observations, D, Xi, and the Xi are drawn from a probability distribution of the data. Now, Xi are vectors, and in my talk, also for the sake of illustration, let's imagine that these Xi's are images. Okay, so we will work mainly with image data. It's more sexy to show, and it's easier to understand. And also, this gives you also a flavor of what are the challenges that we are going to face, because these vectors are going to be very big dimensional vectors. So the first problem is density estimation. And what we would like to do is to receive some unseen piece of data, an unseen image, and determine whether this image belongs to the distribution that generates these images. And this is something we use, for example, in applications like anomaly detection, because this gives you the likelihood that a piece of data belongs to the distribution of the data that is interesting to you. Now, on the other hand, the generative modeling is the key idea is that you want to generate new data that has not been seen before. And all these problems require to learn a model to approximate the unknown data distribution. Now, these seemingly abstract problems might raise an eyebrow. What are they useful for? And there are many application examples, some of which today are really revolutionizing many sectors of the industry. For example, the creative industry, producing images, videos, music, text out of the blue. Actually, at the end of the talk, I will show you how these models can be guided and actually be multimodal. That is, you can give a text input describing something that you want to obtain, and in return obtain either an image, a movie, a video, etc., etc. These models have been also successfully applied in the ICT industry, for example, mainly in anomaly detection. Our group work in close relation with the telecommunication systems department, and for this reason we have applied these ideas in projects that are related, for example, to 6G architectures. And I will spend a few words on these applications in mobile communication networks. And we have projects also with the automotive industry, whereby there are many issues related to the reliability of the sensors that are deployed on the cars, like cameras, lidars, etc., because those sensors, if you're not talking about Teslas, but in our case, we work with Renault, and these are cheap cars and the cheap sensors, so they can break. And so what can we do to supplement and make those systems more robust with this kind of techniques that I'm going to present? Now, just to set the expectation right, the focus of this talk is mainly on the methodology and not so much on the applications. I hope this is okay with you, but if you have questions, don't hesitate. I can go either way, either more on the applications or explain more the methodology. All right, so the current approaches to address these problems that I just mentioned are typical. I hope some of you are already familiar with techniques such as variational autoencoders, normalizing flows, GANs were very popular, still very popular, generative adversarial networks, autoregressive models. So all these methods exist, but we have a problem. And the problem is called a trilemma. When you want to generate data, you want three properties. The first is that you want data to be high quality. If you think about an image, it has to be a high quality image. And another property you want is that the kind of samples you generate with these models to be diverse. You don't want to generate always the same looking face. And the third, you want something that generates images fast. And unfortunately, the current models available in the literature, they are very good in generating high-quality samples and being fast, but they have problems. They struggle with diversity. And this is the strong point of the kind of models I'm going to present today. They are capable of generating super high-quality images with a lot of diversity. And as a spoiler alert, you know already what is the problem with these models. They are not super fast. So a lot of people are working on these issues. Now, we need some basic ingredients to cook up our generative models. And we will start with a basic tool that is required, that is the study of stochastic differential equations. And this is where the connections between machine learning and physics appear. Now, when we work with the stochastic differential equations, we write nice formulas, everything is super elegant, but at the end of the day, we need to implement this stuff on a computer. And so we need some discretized algorithms that, in some sense, simulate those stochastic differential equations. And so I will need to talk briefly about numerical integration schemes. There are many of them, Euler methods, Runge-Kutta, and so on and so forth. These are actually super easy algorithms that you can implement in few lines of code. The analysis of these algorithms is another story, but the implementation is super easy. And so I will spend a couple of words here and there. If you know about numerical integration, super good. If you don't worry. It's not going to be mandatory to know all the details. And finally, we couldn't go without a bit of deep learning. So we will talk about some of these models that require function approximations. And so we will use deep nets as functional approximations, and I will give you some details. Now, in the interest of at least the first part of my talk, you don't need to know what is the architectures, the hyperparameters. These are nitty-gritty details. They're super complicated at the end of the day. But for now, let's assume that someone gives us an architecture. We call it a deep net. It approximates a function, and we are happy with it. All right, so as promised, I need to spend some time on stochastic differential equations. And here on the screen, you have an example of an SDE in expression 1. Let me play with this pointer. Yes, there you go. So an SDE allows us to study dynamical systems and the evolution in time of dynamical systems. They have been applied and studied in many different engineering fields, of course, physics, chemistry, industry in general, finance. Here I have just a nice picture to illustrate that people in physics and chemics, for example, use these SDEs to study the diffusion of food coloring in water and how you start from a drop of food coloring in the water and how this diffuses and creates like clouds. And these kind of mathematical expressions allow us to understand and to study the evolution in time of these physical processes. Now, in this expression number 1, we have two main terms. One term it's called the drift, and it's related to the way you want to model your physical system and how it evolves in time. It could be the position in space, in a three-dimensional space of a particle, for example. And then you have a randomized term, which is the diffusion term, which involves the use of a stochastic process, which is called a Wiener process, or we call it also a Brownian noise, an infinitesimal Brownian noise. And this constitutes the equations that we use to study our systems. Now, there are two major issues. The first is that since we have this Brownian noise term, our equation is almost surely not differentiable anywhere. And so new rules of calculus needs to be invented. And luckily, some time ago, a bunch of people, including Ito and Stratonovich, came up with some new rules of calculus. Under the hood, we use Ito calculus here. I'm not going to go into the details of this thing. It's super hairy, super complicated. I'm not even sure I can tell you all the story. So for now, just know that we rely on Ito calculus for this kind of equations, the study and analysis of this kind of equations. Another problem is that in physics, for example, or if you want to study the diffusion of food coloring in water, you are in a three-dimensional space, and things are somehow more tractable. Our problem is that the dimension of these vectors x's that you see here, these are not the position of particles in space. These are images, and are very big vectors. So high dimensionality complicates even further the problem. All right, now, we have a stochastic process that evolves in time, and this induces a time-varying probability density, which means that basically when you are used maybe from first-year university to use differential equations to study how a body moves. I'm pretty sure maybe some of you remember harmonic oscillators, the pendulum, etc. You can write ordinary differential equations to study their motion. And you know exactly in time where the pendulum is. Now, the problem is here, you don't know exactly the position. You have a distribution of possible positions. And so we need to study the time-varying probability density of this process. And luckily, there are some famous equations that are called Fokker-Planck equations that allow us to do that. And when it exists, it allows you to find what is the stationary distribution of these processes. Now, what is the take-home message in the interest of this talk, which is not a lecture on stochastic differential equations? We can actually engineer these equations you saw before, because we are not actually simulating any real physical system. And so what we are free to do is to choose the phase of this f function, this D matrix, etc., such that it is convenient for us. And so we can engineer the SDE, and I have an example here that is something that we will use later. You can decide that your function f is the negative gradient of a function, e, let's call it e for the moment. and that your diffusion matrix D is just identity matrix, super simple. And with Fokker-Planck equations, you can calculate the steady state distribution of this process. That is, the limit for an infinite diffusion time of these processes is proportional to the x of our minus our function. And this is a very useful property because it allows us to manipulate those SDEs to behave the way we want. Okay, so we can manipulate those SDEs, and we will also use another very interesting fact. You can invert the arrow of time. And so if you think about the food coloring picture here, what we can do is to invert the arrow of time of this SDE that describes from the drop how the cloud of food coloring emerges, and we can take the cloud and go back in time and find the drop at the very beginning of the diffusion process. And so this is going to be a property that we will use very soon in my slide. Now, okay, we have the basic ingredients. How do we use these tools to model and to solve the problems I mentioned at the beginning? And my journey begins with energy. So energy-based models are a very general and flexible method for density estimation. They can also be used with some tricks for generative modeling. But now let's focus on density estimation. So the key idea is to associate an energy, which is going to be a function, to each data point of my data set. And this energy function is a parametric function with parameters theta. We can then define the density associated to this energy of a given input x, p theta of x. And you can find the expression here. There you go. The expression here, expression 3, where we define the energy, the density associated to a data point. You can see that our density is going to be parameterized by the same parameters of our function. Now, we want to have a valid density, so we need to satisfy some constraints. That is, that the density needs to be positive, and it has a unit integral. And this is why we have this normalization that is going to be problematic, by the way. So the normalization is computed as this. Now, what is interesting about this approach is that any parametric function can be used to solve the problem. And then in particular, what we will use is neural networks. And so basically what we are doing is to transform a problem of density estimation into a problem of regression. And regression we are more acquainted to. It's a bit easier to work and think about regression. And of course, when you want to estimate the parameters of this model, what you do, you maximize the expected log likelihood that you find here in expression 4. And all is good, right? We know how to do maximum likelihood estimation. And the problem now is that this normalizing constant kicks in. And computing it generally is not tractable, because in many problems that we are interested in, first of all, the data is high dimensional. Second of all, this neural network has parameters, and it doesn't have 10 parameters. It can have millions of parameters. So computing this integral is simply intractable. Are we stuck? Can we do something to move forward? And the answer is, well, kind of, yes. Well, in some sense, if someone gave us a pre-trained model, a pre-trained energy function, then we can use it as it is. We can compare two data points, x1 and x2, compute their density, and this is going to be corresponding to their energy. And this is super useful in anomaly detection, for example, because you are given two data points, one data point that belongs to your data distribution, the normal behavior of your system, and one data point that does not belong to the normal behavior of your system. And with this energy function, you can compare and decide what is normal, what is not normal. However, for training these models, we need to solve the problem of this normalizing constant, because maximum likelihood estimation, what does it mean? You need to compute the gradient with respect to theta of the expected log likelihood. You have here in expression 6 our nice expression, nice formula, where we have our problematic normalizing constant over there. Now, wait a second. We can play some mathematical tricks and just plug in the definition of z into this part of the expression and realize that we can rewrite it as this one. So it's like we are hiding the normalizing constant into an energy term. And so we can compute an approximate unbiased estimate of our gradient using Monte Carlo techniques. And so this is fine, right? Because we got rid of z. We have a nice expression here, which involves only gradients of our energy, and then we can use this gradient. However, we need to pay attention because this approach requires sampling. Now, this part of my expression, it's super easy. We are computing an expectation with respect to p data, that is my training set. And so I can just, randomly pick some data from your training set and compute this part. How do you sample from p theta? And this is more problematic. Now, finally, we can put into practice what we just learned about stochastic differential equations. And to sample from p theta, we use SDEs. In particular, we use Langevin dynamics. And the form of a Langevin dynamic process is exactly the same form of equation 1 I showed you before. And what we will do is to set the drift term as the negative gradient, pay attention, with respect to x, not to theta, of the energy function. We set the diffusion matrix to the identity, and then we use our Fokker-Planck equations to compute what is the stationary distribution. And surprise, surprise, the stationary distribution of this process is going to be exactly our p theta. So it's going to be an iterative process. We need to simulate, use numerical integrations to, for example, using your Euler method, to get samples from p theta. And by doing this, we will be able to compute our gradient of interest. Right, but we introduced some complexity because now we have an optimization procedure that has two nested loops. You have an inner loop where you need to compute samples of p theta, and then you need to simulate an SDE. It's simple to implement, but it's not cheap at all, computationally speaking, because you need to do many iterations. And then, once you have the samples, you need to compute the gradient with respect to theta in the outer loop. And this means that a naive approach to maximum likelihood estimation for energy-based models has slow mixing times. Are we doomed? Well, can we change perspective, maybe? All the problems we had were coming from this normalizing constant. And some people in the past, Professor Ivarinen, in 2005, came up with this very clever idea of using something that is called the score function. Now, I'm doing a bit of abuse of notation. In statistics, the score function is the gradient of the log of our density with respect to theta, whereas here we are playing a trick, right? We are computing the gradient with respect to x. When you substitute the expression of p theta inside this expression, you will notice that because we computed the gradient with respect to x, the normalizing constant goes away. And then we got rid of it. And then we can use score matching, which is equivalent to density matching, to solve our problem. And this was the major result from Ivarinen in 2005. So we can replace the maximum likelihood approach by using Fisher divergence. You have an expression here. Now, all this seems fine, but it's still impractical, right? Because you need the knowledge of this quantity. And we are trying to estimate this quantity, so it's not going to fly. We needed to play some additional tricks to use Fisher divergence. And so some clever tricks are to rewrite equation 11 such that we get rid of this offending term, and we end up with this seemingly complicated expression that is fine. We have all the ingredients here, and we have another problem. We needed to compute the trace of the Hessian of our log, our score. And it's not cheap at all. And so that's exactly the point where, in the history of this kind of modeling techniques, people came up with zillions of ideas. First of all, they tried to simplify the computation of this term of equation 12 by doing random projections. Then they realized that once you solve this equation, you get theta that minimizes the Fisher divergence. Then you need to use, again, some SDs to sample and generate your data. But you have a problem, right? Because you are taking an expectation with respect to your data set. And your data set is going to be distributed on the, imagine that we are talking about images, right? It's going to be distributed on the manifold where you have the data. But it doesn't cover the whole manifold. And so people started thinking about, yeah, you know what, let's insert some noise. And this noise plays a crucial role in what I am about to tell you about. Okay, so we have all the ingredients. Now let's move to the meat of my talk that are score-based diffusion processes. So the key idea is super simple. We have data. What if we can devise a procedure that, according to some well-defined process, destroys the information and gradually transforms it into noise? Could we define the inverse of that process that allow us to go from noise back to our data? So we have a picture here. This is the typical, 101 data set MNIST on digits. We have our number 9. We start from data. We need to define a process that gradually destroys the information. Here we have a realization of something that really looks like white noise. And then we want to be able to learn how to go back from this noise to our initial image. If we could do that, then we could sample, it's moving weirdly, we could sample from the noise some random sample and just use what we learned to reverse the process and generate new data. And this is exactly how these processes, these models, the generative models work. Now, let's try to put some more meat into this key idea. We have a forward path that is going from the data to the noise. That is actually an easy path. We sample from our data distribution. We add some noise. It's the simple thing we can do to destroy information. We add noise according to a schedule. And we will arrive at a simple destination. Simple here means that it's easy to sample from. And ideally, we would like that to be some form of Gaussian noise, white noise. And this is called the forward diffusion stochastic differential equation. And we will do something clever. We will engineer it such that this SDE is affine, because this will allow us to analytically solve some of the processes, and we will not actually need even to simulate this SDE. The reverse path, so going from noise back to the image domain, is actually harder. We start from a generic sample at the noise, and we gradually need to learn how to remove noise until we get back to the image domain. And this is called the backward diffusion stochastic differential equation. And unfortunately, it's not going to be affine. Yes, there's a question.
Well, it's not a question, it's more a comment. If you could go back, what I don't like, you are sort of explaining it in a standard way. What is, to me, incorrect is that in your previous slide, the thing on the right is noise. It's not noise. It's just different coding of the image by a sample from some Gaussian distribution. So what you are adding is noise, but what you end up with is not noise. It's in one-to-one relationship to the image. It's just a different coding.
So what you say is particularly, it's unfortunately partially correct. I agree with you, but when you do the forward process, in theory, and this is where the theory is different from practice, you need to diffuse for an infinite amount of time. And when you diffuse for an infinite amount of time, there is zero correlation between where you end up and where you start from. In practice, you are right, you need to simulate for a finite amount of time, and so there will be some correlation, and that's an approximation that we are making. And that's something that is we can quantify, and I have a couple of slides on that.
Maybe what is counterintuitive that you have an arrow which you call information destruction.
Yeah.
You are showing in the training that it's reversible. So to call some process before destroying information and then actually it's a reversible process, I would never use it. It's to me misleading to people who don't know what's going on. Because you in training, you try to say, I will go from 9 to this noise.
Yeah.
Back to 9. It's a reversible process. So nothing was destroyed. You just deformed the distribution. To me, it's much better to think about it as transforming a distribution of the original set of images to a Gaussian distribution on the right.
Yeah.
And not at all to speak about information destruction and about noise. Noise is added to the image, but the representation that you end up is not noise. It's actually retrievable, the 9, from that.
As I told you, there is the physical principle where you actually destroy the information because you simulate for an infinite amount of time. You agree on that, right?
You can't show to the audience something that you say destroy the information and yet it is reversible. So this would be a paradox, contradiction in terms, and that.
Okay. So I'm saying that if you have an image which says we destroy all information and then this is reversible,
yeah,
it creates a contradiction in terms, which is a paradox, and somehow we have to say, aha, where is the paradox coming from? We actually don't destroy the information, we just do something in the direction which has kept the information, but transformed into a distribution from which we can sample, and in training, the nets and actually the score function will achieve this reversibility and the ability to sample from the Gaussian, which is what we really want.
So let me ask you a question. When you sample from what you call noise, okay, what is the information that is contained in that sample? When you sample from a Gaussian distribution,
there are two words. Okay, one thing is what you are adding to the image, which is noise, and the second thing is what is the result of the process, which is some realization of white noise, which can be decoded in some way to get the original image.
That's needed. Otherwise, what can you learn? You need, as you said, no, you need to learn the score. And once you learn the score, you use this model in inference time, right? When you use it in inference time, you sample from noise. Do you agree?
Okay, so I think these... okay, maybe the difference is that every sample which is from some distribution which you happen to call noise, I think the word noise should be used carefully. So you could say I sample from a Gaussian distribution, and to every sample there is an image from my original domain. And whereas when you are transforming the image, you are really adding noise, which is some random set of numbers that you don't really care about. And you sample that again and again from a random generator. Whereas if you are sampling from the destination distribution, you want to really retrieve an image in the original. Okay, but let's leave it offline.
All right. Okay, so now we can be a bit more formal about what's going on in our processes. We have the forward SDE that you have on the top. And as you can see, this is a special form of the equation 1 that what we saw before. And we have the drift term that is a simplified drift. And what happens, this is something that we had discussed right now, is that you keep adding some realization of a Brownian noise to your data sample. And in theory, I mean, I cannot draw it, but in theory, you need to do this path for an infinite amount of time. You will end up in a stationary distribution, if it exists, that you can compute. But in practice, we will see that you cannot wait for an infinite amount of time, so you need to do some approximations. And the reverse process was defined some time ago by some bright minds, and when you look at it, you see that it looks like the negative of the forward process with these two terms, but we have an additional term in red here, which is our friend, the score. And we will exploit this fact to train what we just call the score network, which is going to be an approximation of this score, to generate new samples. Okay, so unfortunately, we need to accommodate some approximations. First of all, we are not in an infinite time regime. We are in finite diffusion times. So if, in principle, under some conditions, the stationary distribution is distributed according to a Gaussian zero-mean identity covariance, in practice, we will need to select a large diffusion time. In the literature, people say it has to be large enough without specifying it further. And this means that we will commit an error. When we will use a sample from this stationary distribution to go back to the original domain, we will make a mistake. And second, the score function is not known. So we will need to approximate this function over there, and we will use a deep neural network to do that. So this is the notation I use to express my score function. And one thing I would like you to notice is that it accepts as an input not only the data, but also an indication of what is the noise level that you are using. And here I'm cutting a lot of the math because we don't have time to go into the details. But people that came up first with this kind of models found a way of defining a training objective, which is called the continuous score matching objective. And you have it over here. So this is what we use to train our model. Now we can put our neural network here on the process, and everything seems fine. Now, all these seem a bit abstract. How does this work in practice? One way of seeing is that, first of all, we talked about the forward process being a particular process because it's an affine process where we have the ability to compute analytically a conditional sample. So conditional means given this input image, by diffusing this input image by this amount of time, what is the noisy version of the image? And this is the expression that we can use to compute our conditional sample, which basically means that we do not need actually to simulate the forward SDE. So in practice, very basic terms, when we want to train our score network, what we can do is actually to see this as data augmentation. So we will sample our data, all our data from our training set. We will sample, at least to begin with, uniformly at random some diffusion time. We will sample many Ws here. And we will produce a data set of a clean image with many versions of it with different levels of noise. And the score network becomes an implementation of a denoising autoencoder. So what we are really training is a network that learns how to remove noise. Okay? Now, some people argued that uniform sampling is not the best idea to go. People studied these diffusion processes and found that there are different phases, especially in the generation phase, whereby at the beginning of the reverse path, you have the ability to inject some semantic in the kind of data that you're generating. And when you are closer to the end of your anti-diffusion time, you're just refining your image. And so there are people that suggested to use importance sampling or to use log normal sampling to exploit these observations. So in practice, that's it, right? There are different kind of parameterization. In this toy illustration, I'm showing that you're basically learning how to remove noise from an image. Other parameterization involve you learning the actual noise you're adding to the image. All these parameterization have pros and cons, and many studies in the literature appeared. Now, to generate sample at inference time, you actually need to simulate the backward SDE. And we can use, I mean, I have some sort of animation that is probably easier. You start from a sample from your Gaussian distribution, and you use the expression of the SDE. You use the score network that you have learned during training, and you produce. So you start from a sample from your Gaussian distribution. You produce a less noisy version of it. You use it as an input for the next round, you obtain a less noisy version of it, and so on and so forth. And finally, you obtain a sample that you generated. Okay, so what can these models do? Now, I will have to move quicker because I want to leave some room for discussion. They're amazing. They can generate super good looking images. A lot of people that work in this domain use celebrity faces to generate. There are many data sets that are fancy. You can see that there are some details that are maybe not completely perfect. Look at the eyes. But still, I would say that these are amazing, amazing pictures. So this is one of the reasons why a lot of people out of academia went crazy about these models, because they actually can generate super nice pictures. You can do class conditional generation, so you can slightly modify the diffusion, the inverse diffusion process that we just saw, such that you can generate images that comply to a given class. You can do imaging painting, for example. So here we have examples of another kind of data set that is frequently used. And you have all sorts of occlusions on the image. And here you have samples that are likely samples of the original image that you have here on the left that recover the occluded part. Now, in the image domain, could be sexy, could be interesting, but there are many industrial applications for this. For example, in the automotive domain, we have exactly these problems, right? You have a camera installed on a self-driving car, and there's a piece of dirt. And what do? Can you use in painting to remove the piece of dirt? And people are looking into applications of this kind, of these models. You can do image colorization, and so on and so forth. Now, what are the challenges? And some of those challenges, we are trying to address them in our group at Eurocom. So for sure...
Excuse me, can I have a question about the method still?
Yes, sure.
Oh, great. So you are going now fast ahead with the applications and implications, but still about the method. I think it's not fully clear. What is the difference, for example, to GANs? So the GANs, each point in the noise space, in this latent code, they will map all the time to the same image. But here in this diffusion process, the reverse process is stochastic, right? So if I start from some noise in this noise space, will I arrive to the same image or similar images, or I will generate completely random image from the data distribution?
So when you sample from noise and you obtain different samples, you land into a different image. And this, I'm pretty sure it happens with GANs as well, right? When you start exactly from...
No. Wait. GANs learn deterministic mapping from some noise latent space to the image space. And every time I pick a point in this latent space, I generate the same image. Yeah, unless these are some GANs with this progressively adding noise.
That's true, but that's if you take exactly the same point in the Z, in the latent space, right? If you choose a different point in Z, you obtain a different image. So what you're saying is, the question would be, if I use the very same sample from my Gaussian and run the diffusion process twice, do I land into the same image or not? And
yes.
I'm not completely sure. What I think is that because you have this term here, which is additional noise that is going to define a different trajectory of the SDE, you may end up in a different image.
So you say the forward process fully destroys the information. So that means that this final state kind of doesn't matter. It's a random sample from the noise in there.
No, it's not the same. It's not the same thing. The forward process. Okay. So the forward process, the samples that you have. So if you imagine the forward process, you start from the image. You have this arrow that goes to what we call x of capital T, which is the ending distribution, and small t is a different time instant on this diffusion process. So here, this is how you are destroying the information. You are adding this noise to your process, to your image,
yes,
right?
Yeah.
So, as we were discussing before, in principle, if you were to diffuse for an infinite amount of time, you would really end up in something that is completely not correlated with the starting point. In practice, that doesn't happen, and you end up in a distribution that we pretend it's going to be the end distribution, but it's not going to be. I have to anticipate maybe something. Let me show you this. Yes. So this figure could be helpful in our discussion. I will explain what is this slide about maybe later. I don't think I will have time. So you have this diffusion process. You start from your data, you diffuse, you end up in a distribution that is defined by the diffusion time, capital T. Now, here in this figure, I'm already assuming that we are going to make a mistake because the diffusion time is not infinite. If you had a perfect knowledge of the score, you can go back exactly in your data distribution. Now, if you could only access an approximate version of the score with this blue line, with your score network, then you will not end up exactly in your data distribution. You will be at some distance that we can measure in terms of KL divergence. Currently, the diffusion processes, score-based diffusion models from the literature, use a distribution to start from that, sorry, it is over here, that is not the same distribution of a diffusion process, but they assume, they make an approximation, they assume that even if you diffuse for a finite amount of time, you can sample as if you diffused for an infinite amount of time. And so they start from this distribution that I call p-noise, maybe it's hurting, and they use the approximate score to go back to the data distribution. And as you can see here, it's a schematics, but there is another kind of distance from the data distribution they land up in and the actual data distribution. And so what we did in some of the work is to say, you know what, you can do multiple jumps, right? So you can train an auxiliary model to start from this noise distribution and to try to amend, to mitigate the mistake that you're doing by sampling from noise, whereas you didn't arrive, you didn't diffuse for an infinite amount of time. So you arrive at a distribution with our auxiliary model that is closer to the distribution that you end up with by diffusing for a finite amount of time, and then you use your score model to arrive at that data distribution that is going to be a bit more similar to the data distribution done with the standard diffusion models. So I'm sorry, I'm literally running out of time. I just really would like to point out that this is one of the work that we did on studying the implications of diffusion times, what are the trade-offs, and there are trade-offs actually. And these trade-offs derive from a different interpretation of the optimization objective of our score models. We can prove that there exists an optimal diffusion time, and however, choosing an optimal diffusion time is not our goal. Because it's costly to find the optimal diffusion time. What is our goal is to find a way to mitigate the mistake that we do with this term. The fact that the starting distribution from which we anti-diffuse is not going to be a noise distribution, but because of a finite amount of diffusion time, we need to compensate for this error. Another kind of work we do, this is very recent, is to move out from the data domain and move to the functional domain. So what we have done is continuous time functional diffusion processes. And the reason why we're working on these is because vanilla diffusion processes are actually not so easy to parameterize. They're super easy to implement, but then you need to define the architecture of the score network, and this is far from being trivial, actually. Current architectures are super complicated U-nets with attention mechanism and so on and so forward connections, etc., etc. And so the idea is, well, what if we move to a functional domain? Would this have an impact or an improvement on the way we diffuse data and generate data? And some piece of work, we could have an entire talk about implicit neural representations, neural operators, etc., etc. Some piece of work allow us to transform our real-life data into functions. And then what we had to do is to say, okay, you remember the stochastic differential equations that we saw before? These were in a finite domain of images, for example. What we had to do is to define the forward and the backward process of these SDEs in infinite dimensions. And so once we defined and proved the existence of the more difficult part, the backward diffusion process in infinite dimension, then we said, okay, but which kind of functions are compatible with this way of modeling diffusion and anti-diffusion? And we came up with an extension, a very simple extension to the sampling theorem to show that we can focus on a subset of all possible functions that satisfy some constraints that we have. We needed to extend also the Girsanov theorem that allow us to find the optimization objective of these models. And what we ended up is with heavy-duty math, but a very simple computer program that can generate images as the ones that I showed you before, but instead of using a score network that is a million parameters, 100 million parameters score network, we use a multi-layer perceptron with 6 layers, and that's it. And so this is one of the big advantages of moving to the functional domain. In addition to these advantages, we also inherit from the fact that by working on functions, we become scale-free, resolution-free, data type agnostic. So a lot of different kind of data can, and not only images, can be used with these models. And so this unlocks a lot of applications. We work also on multimodal diffusion processes where we want to set apart from, probably you have heard about these tools, Stable Diffusion and Michiardi and so on and so forth, that allows you to write some text and generate a corresponding super good looking images, an astronaut cat on the moon, and you get an image like that. The problem is that you cannot do the other way around. And we would like to have a truly multimodal approach to diffusion processes, and this is what we are working currently on. And this is my conclusion. We had a brief tour on score-based diffusion models. They achieve superior generation quality than the state of the art, and they unlock many industrial applications. Yeah, I saw that there was a question. I just couldn't see the full question. I will address it later. One of the main problems that we currently face ourselves is that we still are far from efficient methods. This is a quote from a couple of years ago, paper from colleagues from NVIDIA Labs in Toronto, where in the appendix they show what are the computational resources that they needed to train. This was a score-based diffusion model in latent space. It's another kind of work I didn't have time to talk about. But you see, this is 350,000 GPU hours. It's crazy. I mean, most of the people, at least we at Eurocom, do not have access to this kind of resources. We are just lucky if we have a bunch of GPUs. And so maybe with constraints come the willingness to improve over the methods that exist that so far are still super expensive. Now, I'm going to stop here. And thank you for your patience and for your attention. If there are any other questions, I saw that was
thank you very much, Pietro. Let me. There are some questions in chat from Radim Špetlik, if I do remember him correctly. So if he's still online, please can you ask the question or questions? And in the meantime, I will distribute.
Okay, can you hear me?
Yeah.
Great. Hello, thank you for the presentation, very nice. So the first question is to the EBM. So the whole EBM derivation with the Langevin dynamics is nice, but could you comment on its usefulness, since most DDP and DDIM authors' papers just use something they call simplified loss, which is just MSE of the prediction and ground truth. So does it make sense to even introduce it?
Well, let me go back. Yes, of course, it makes sense. First of all, because these tools, let's fix here. These tools are actually great for applications where you're interested in density estimation. So the bulk of my talk was actually a bit tainted by generative modeling, whereas here, clearly, your application domain is more density estimation. So I gave a couple of examples. Maybe I have even backup slides. Let me just double check, where I can just show you what does it mean. Yeah, it's good enough. What does it mean to use energy-based models for density estimation? So here we have some data samples that belong to our data distribution, and as a consequence, they have a very low negative log likelihood. So here I'm taking the negative log likelihood. It's the same thing. I mean, here we are looking for a small value of negative log likelihood. Whereas samples that do not belong, here I'm producing samples that seems Gaussian noise. In reality, what we do generally for testing the ability of our density estimation to be useful for anomaly detection, for example, is to take if you are familiar with fashion MNIST or other kind of data sets that resemble a bit these digits, but instead they are clothes, trousers, shirts, etc. And what really your objective is that samples that belong to a different data distribution have a high value of negative log likelihood. And this is how you distinguish between samples that belong to your distribution and samples that they don't belong to your distribution. Now, in applications like for most of anomaly detection methods, you will need to define thresholds. There is much more to it when you want to apply them in this context. But these are very important bases. So I still think it's a useful model. We have used it in industrial applications with some partners. It is true that it's not super trendy. I mean, you don't find so many research papers lately published at NeurIPS or ICML, etc., on energy-based models. A big proponent of energy-based models is Yann LeCun. So, in my opinion, they are cute. They were fitting the narrative that I wanted to build with this presentation.
Okay, thank you. I would like to have another question if I can.
Sure.
So the next question is, would you comment a little bit more about the function diffusion processes, about the thing that you mentioned that you're working on?
Absolutely. Okay, there you go. Right, so let's start from what you have here in the middle of the slide. So before even talking about diffusion processes in function space, so in the infinite domain, let's try to motivate one possible approach to move from data to functions. And there is a nice paper that's actually called From Data to Functa, where they are trying to propose to the community to move away from the typical data sets that we use in machine learning and instead to store them as functions. And so here you have an example with images. You have examples with data that is like here, it's the temperature on the globe. Here you have 3D point clouds. Here you have 3D objects. So the idea of these models, it's actually, again, some sort of regression problem, right? You have a neural network that is a simple MLP, where as an input, you provide the coordinates of the pixel locations on your image. And as an output, you put the RGB values of that pixel in that position. And what you want to do is to learn the functional mapping between the coordinates of an image and the intensity of the pixel in that location. And so given a single image, you can learn a neural network, and you can use the weights of this neural network, the full weights of these neural networks, to represent this image. Once you have these weights, it is kind of easy to imagine that you can give as an input some different coordinates. They are, for example, very used in super resolution applications, right? So you imagine to discretize differently your image domain to introduce a more fine-grained grid of points. You give this input to the network, and the network was trained to predict the value of the pixel at this new coordinate. And as a consequence, it becomes super easy to do super resolution, imputation, and so on and so forth. Now, you may say, wait a second, then for every image, you need to train a different neural network. It becomes pretty costly, right? And so in the literature of implicit neural representations, a lot of people worked on the concept of modulation. That is either to apply meta-learning or to use some auxiliary networks that are called hyper-networks that learn how to modulate, where modulate is used improperly here. I know that the public is also from telecommunications, so it's not exactly the same kind of modulations, but to move the weights of the base network according to different images. And a lot of people applied these ideas to image compression, for example. There's a big branch of research in using implicit neural representations to compress images. Now, what instead we wanted to do is to say, okay, now if all these diverse kind of data can be represented at arbitrary resolution, at arbitrary scale, as functions, then would it be possible to build a generative model that instead of working in the data domain, can work in the function domain? And what we did is to look up in the physics literature. A lot of people already worked on that. We contacted even an old professor. He's retired, but he was very kind to reply, Da Prato, who explained a lot of his work on functional diffusion and pointed us to the right literature of how to derive the backward process, which is the key to use these processes in generative modeling terms. And as a consequence, we started like that. So we started by saying, is it even possible to define diffusion processes in functional domain? We were not the first. We just collected all the different work in different kind of literatures with different notation. That was already a lot of work to understand and unify the notation. And then at that point, we said, okay, but wait a second. Can we just use any kind of functions to be used in these diffusion processes? And the answer is not always, because for the reverse process in infinite dimensional space, you needed to satisfy some constraint. And this limits the kind of functions that you can use. So not all functions are compatible with these infinite dimensional diffusion processes. And so we defined a sampling theorem to decide whenever it was actually possible to use the kind of functions we were able to produce with implicit neural representations in these diffusion processes. And then what remained to be done is to follow the same steps that have been done in the literature of vanilla diffusion processes to see if it was possible to work. And we needed to move from the abstract formulation in the infinite dimensional domain to something that we could implement in a computer program. So we implemented everything in JAX for the story, and we came up with our own definition of the optimization objective. And what we did is to realize that the score network that a bit like in a toy example, for this talk, I explained that you can see the score network as a denoising autoencoder. Then we said, okay, but a lot of people in the literature of implicit neural representation used also these implicit neural representation networks as image denoisers, and they showed that they work super well. And so we said, you know what? Maybe we can use just the implicit neural representation as the score network. And this is what sets apart our work from a bunch of recent work that popped up in the same days and the same weeks as we put our work on Arxiv. They use a different kind of functional mapping. These are called neural operators, more precisely neural Fourier operators. But what we did is something actually simpler. We use these implicit neural representations, and the main reason for us was computational constraints. We don't have 20,000 GPUs to play with, and as a consequence we were constrained by using smaller models, smaller networks, simpler networks. In our group, in my group, we are not deep learning ninjas. We don't know all the tricks of the trade and how to tune the learning rate. We don't have training babysitters, etc., etc. And as a consequence, we need something simple. Something simple that doesn't require so many resources and that still is capable of producing decent results. And this is what we achieved with this work.
Thank you. Are there any questions in the room? Or also in Teams? No? Okay, then thank you again, Pietro, for a very nice talk. And thank you all for coming or joining through Teams. And have a great day and weekend.
Thank you.
Thank you. Thank you.